Hi, everyone. Welcome to this webinar. This is the first official RSWall webinar. RSWall is our new program at Rocscience that we released in March, and it's a retaining wall design program. And this is the first introduction webinar for the RSWall program. My name is Sina Javankhoshdel. I'm the team manager of the Limit Equilibrium team, including a slide 2, a slide 3, and RSWall software. And in this webinar, I will be presenting about these programs. About Rocscience, we are the world leader in developing innovative 2D and 3D software for civil, mining, and geotechnical engineers. We have like over 25 years of experience of the development. We have grown to a team of more than 80 people in our main office in Toronto, and we have 4 offices and representatives around the globe. And we have over 10,000 customers as well. Rocscience has 19 programs. RSWall is one of these programs that we recently released. So these 19 programs, they are for different applications. As you can see here, they are integrated with each other. This is the Rocscience's software ecosystem. And you can see RSWall is introduced here. It is integrated with the slide software, which I will talk about it in this webinar. And other programs like a slide 2 is integrated with the slide 3, RSWall, RSlog, RS2. So this ecosystem is very important because all these programs are being developed here in our main office in Toronto, and we can integrate them and take advantage of using different approaches for different applications and integrate different programs. In this webinar, I will be talking about 2 of these programs, RSWall and Slide 2, mainly RSWall, but since RSWall is integrated with the Slide program, I will talk about Slide 2 briefly as well. Okay, let's get started on the background of retaining walls in general. Their application is to hold the back soil, and they can accommodate steep changes in elevation as well. These structures, their application is for highways and roads, for bridge abutments, erosion control, and other types of slopes as well. The typical types of retaining walls, these are the ones that we include in the RSWall program. There are other types of retaining walls as well, but these 7 different types are the ones that we include in RSWall. They can be segmentally built or massive, like cast concrete. And for very high walls, typically they are reinforced. And basically, by reinforcing them, we are making soil to become part of the wall. I'll talk about these different types later. So, what are the typical failure types of retaining walls? This image shows for MSC wall, which has reinforcement as well, so it has one additional level of failure mechanism. But basically, the retaining walls, they can fail externally, like sliding, overturning, and bearing capacity. And they can fail internally, basically rupture of reinforcements or pull out. And they can have overall failure, stability failure as well. So these are the typical types of failure that I will talk about them in this webinar. So let's just look at the brief flow of the design of retaining walls. As I mentioned, RSWall is a design program and it's based on standards. And so that's the flow of the design based on these standards. So the first step would be to pick a design standard, depends on your region, depends on what the standards are accepted by authorities. And then You should know the limitations, you should know the methodologies that they use in these standards and their limitations as well. Then we go to geometrical requirements. You need to define your wall height, wall length, and topography. The geometry is similar to the wall that I put the image here. Then you need to do site investigation to find your soil parameters, seismic parameters, groundwater condition, even the type of wall and material selection. After that, we need to know what is the stage of our loading requirements. It can be permanent loads, dead load, live loads, and different types of loads that we have to specify. After specifying all these, we need to do an iterative procedure for the shape and reinforcement of the walls to satisfy factor of safety or CDR. Factor of safety is for ASD design, allowable stress design, with assumption of not having any load and resistance factor. CDR is for is factor of safety, but in the LRFD approach, load and resistance factor design approach. Then, after satisfying the internal and external failure mechanisms, we need to ensure that overall stability is satisfied as well. And at the end, once we are happy with the design, we have to create reports and drawings and verify with hand calculations as well. So this is a procedure, and we try to follow this procedure in this webinar as well. Before going to the program, I would like to talk a little bit about the design and the theory behind the calculations of the in the design procedure. So let's talk about design standards first. First of all, engineers must adhere to locally prescribed design standards, as I mentioned before. Basically, design standards, they stipulate the minimum requirements for a design to be considered satisfactory. And design standards often prescribe load and resistance factors. So basically, they are based on load and resistance factor design. This is an example of AASHTO 2020 that you can see all these load factors for live load, for earth loads, surcharge, dead loads, different factors for different loads. So that's the first step. Then let's talk about these failure modes in more details. We for external failure, we have base sliding, overturning, and bearing. Different types of mechanisms. I'll show you detailed equations shortly. Internally can be these and can be in reinforcement. So internal sliding is basically a sliding of along the supports or along the wall courses, blocks, and crest toppling. These two only happen for gabion walls and segmental walls, not for gravity walls. And internally can happen for reinforcement as well, that it can include tensile rupture, pull-out, and connection failure. So these are all internal failure mechanisms. There might be other ways as well. One of them is overall sliding, which can happen, can be shown in a software like a limit equilibrium software, such as a slide 2. Or other types of failure, which can be a failure in the structure of the retaining wall. This one is related to structures, and it's not included in this webinar or in the RSWall program. So the first step to design these walls is to estimate the forces applied to the wall. The simplest way is to assume an active wedge behind the wall, which represents the soil pressure, active soil pressure behind the wall. And there are different methods. I'll talk about it in this presentation. But in general, we are looking to find the active earth pressure force, PA, for our calculations. Ka is a very important parameter, which is a ratio of the vertical to active earth pressure. And there are different formulas in different standards to calculate Ka. However, this simple active planar active pressure is not always the case. When you have cohesion, adhesion, and surcharge, they can change the pressure distribution. Groundwater can reduce the effective vertical stress. Failure wedge may not be planar, and seismic loading affect the distribution as well. So it can be a nonlinear case like this. To estimate the forces, there is a generalized methodology. Basically, we assume the balance of forces, different forces like weight of the soil behind the wall, friction of the soil on the wall, and the active pressure, the other loads, external loads applied to the wall, they are all in equilibrium. Then we solve for the failure wedge angle of alpha that maximizes PA, which is active earth pressure force. And as I mentioned, the failure wedge does not have to be a planar failure. There are common simplifications for different methods, depends on the standard. They pick different methods. Coulomb method, for example, it doesn't accept any cohesion. Ranking method, no cohesion, no soil structure friction. So there is a table, it's in the documentation of the RSWall as well. So different regions, different standards pick different methods. So you should know what in your region, what is the recommendation by standard. Yes, there is a question. Coulomb method considers friction. Yes, I mentioned it doesn't consider cohesion, not friction. There are like different methods like Breach and Hansen is based on log spiral wedge active boundary, and they consider wall batter, back slope angle, soil structure, friction, and cohesion, and they output the Ka value. Coulomb does not consider the cohesion, but it considers others as well. Rank is the simplest one. It doesn't consider cohesion, soil structure, friction, or other. So this is a good guide for you guys if you want to see what method you should pick. How about the passive force? So sometimes in front of your retaining wall, there is a passive soil as well. Depends on the fact that this soil is permanent or not. You can, and depends on the recommendation by the standard, this passive force resistance can be calculated and accounted in the analysis. And there are different methods to calculate this force. To estimate the tensile force in reinforcements, we assume an active zone inside the reinforcement as well. And based on this active zone, we calculate the tensile forces in the reinforcement. There are different methods. The ones that we have in RSWall is simplified method, coherent gravity, or tieback wedge method, and a stiffness method, which is the recent method. Simplified method, it assumes that each layer is responsible for a tributary area of SV. It can be a spacing of the uniform reinforcement or other values. Active stress is calculated as Kr sigma V. Kr is the internal lateral earth pressure coefficient. And it has the same calculations as Ka. And Tmax is being calculated as Kr sigma VSV. So this is the formula. Coherent gravity, it assumes an active wedge behind the reinforced zone and consider external forces on a layer vertical stress. It has the same equation, but determining sigma V is more rigorous because based on these pressures, we calculate the eccentricity as well, and then we calculate sigma. There are different names for it in different standards, and it depends on like some assumptions that they have, and in some cases they are the same. A stiffness method is a recent method for calculating this Tmax. In actually, it's for geosynthetics only, and it considers the entire reinforcing system deforming together, and then it distributes the total force to each layer based on the stiffness of the layer, and this is the formula. Now, for external failure, after estimating the forces, we go to different failure mechanism to estimate the factor of safety or CDR. For base sliding, we compare forces parallel to the sliding plane, and our resisting force is going to be the frictional force multiplied by the normal force due to the weight of the retaining wall. And the CDR, capacity demand ratio, is going to be the sum of the resisting forces divided by the driving forces coming from the earth pressure behind the wall or other loads. Capacity demand ratio of greater than 1 is adequate in LRFD. In allowable stress design or ASD, ratio should exceed the prescribed value, for example, 1.5. Overturning is the resisting moment versus driving or overturning moment. It's a ratio. It's going to be the CDR. Bearing failure mechanism is the bearing capacity versus bearing stresses, and CDR is QR divided by sigma n. And the bearing width depends on the eccentricity as well. And bearing capacity can be prescribed or calculated using Terzaghi's equation. You can define it yourself or we calculate it. And this is the same way in the RSWall program. Tensile rupture is factor tensile force versus factor tensile resistance. It's a reinforcement property, is the tensile resistance. And the CDR is going to be TR divided by TF. Pull-out is factor tensile force versus factor pull-out resistance, and pull-out resistance is a function of pull-out length, vertical stress, and friction of the soil. And this is the CDR. And connection is going to be the factor tensile force versus factor connection strength. And this can be another type of failure. Internal sliding, as I mentioned, it only we only check it for segmental walls and Gabian walls. If there is a reinforcement, it's going to be along the reinforcement. If there is no reinforcement, it's going to be along it for each block. It's very similar to base sliding, but for it can include the interface sliding of the reinforcements as well. Toppling, which is an internal failure mechanism. Again, it is for segmental and Gabians only, similar to overturning, but for that layer of the reinforcement, for that height of the wall. There are other effects, for example, effect of groundwater. Groundwater generally reduces the CDR, can cause other serviceability issues as well. It reduces the normal forces relating to sliding, bearing, tensile force calculations. Hydrostatic forces act normal to the wall boundary. You can see FWA here. Hydrodynamic forces can be added if seismic force presents, and normally seepage forces are not considered. We assume static water pressure at boundaries. For seismic, they have the modified equation for Ka in different standards if you have seismic actions. We have inertial forces which are proportional to internal weight. And in many design standards, they assume that Kv is equal to 0. Only they consider the horizontal earthquake. And if groundwater presents, hydrodynamic forces may need to be added. Depends on the soil porosity. Now, let's talk about RSWall. RSWall is whatever I mentioned so far is available in RSWall, and it's a design program. So we prepared a short video. I will talk over the video to show you different features of RSWall, and then I'll do a couple of demos about RSWall program. So we have 7 different wall types in RSWall: MSE wall, gravity wall, cantilever wall, Gabian walls, abutments, block walls, and wraparound. Block wall and wraparound and MSE, they are segmental walls. We have 7 different design standards: AASHTO, FHWA, NCMA, Australian, British standard, Eurocode, and user-defined standard that can be defined in RSWall. We have all these mechanisms of failure that I mentioned: external, internal, and reinforcement strengths, which is internal as well. We have different methods to calculate active earth pressure, as I showed you before, depends on the standard. This is an image of MSC wall, single segment wall. We have a wizard to create multi-segment walls. So imagine this wizard. These are for different walls, and we create a multi-segmental wall with a 3D view and plan view, like this example. You can create uniform and non-uniform block wall. This one is a non-uniform one. You can create gravity walls. You can see the differential water table in the gravity wall. You can create cantilever walls. We have typical shapes for them. And Gaussian walls as well. You can define different sizes for baskets and angles for the Gaussian walls. You can define bridge abutments as well. You can see different loads applied to the bridge abutment in this example. RSWall, similar to slide 2, has manufacturer library for geosynthetics. Also, it has manufacturer libraries for facing blocks as well. You can define different types of load, including distributed, line load, horizontal, vertical, permanent loads, different types of loads. You can define different geometries for back slope and front face, including user-defined geometries. You can define uniform and non-uniform support configurations. It's a very handy tool here. We have detailed presentation of the results. I'll talk about it in demos. And the most important one, we have the detailed hand calculation. This is not a black box. You can see all the hand calculations. Other important thing, it is directly integrated to slide software, so you don't have to recreate your geometry. Everything will be transferred to slide 2 for overall stability. And at the end, it is very flexible in terms of exporting the geometries or water table or soil properties as a TXF file. So these are like overall features of the program. So what I will do, it's better to show all these features in examples. So I'm going to show you a couple of demos of the program that you know how this program works. Okay, so once you open the program, this is a welcome page, welcome dialog, and you can pick the type of wall that you are interested in and the type of standard that you want. So for example, this is a cantilever wall, and you can pick the standards that you want to model your wall. Or you can start with an empty project, which is okay. As I mentioned, MSC walls, wraparound, and block walls, they are in the category of segmental walls. So any of them that you pick is a segmental wall. I will answer the questions at the end, but feel free to type down your questions in the question section, and I will try to answer them at the end of the webinar. I will specify enough time to answer all your questions. Okay, so for this example, I start with an empty project. I'll go to project settings. Let's see what we have here. We have different units, metric and imperial. And for each one of them depends on, because different standards, they provide different types of units, MPa, KPa, or tons per square meter, different types. So we have all of them. So for this example, I'm going to stick to metric KPa. For the wall type, you can pick different walls here, but I'll stick to the segmental wall. Design standards, just don't get me wrong, FHWA is not a design standard, it's a guide. But some people, they use FHWA for design. So since FHWA is a version of AASHTO, we just put it as a tab here. So if you want your design to be part of FHWA, you just check these options and do the design based on FHWA. There are some advanced settings as well. These are different interpretations from the standards. For example, if you want to use the hinge method, that's a default, but you can turn it off. You can ignore the wall facing weight during the sliding calculations. It's up to you to pick whatever you want. We basically left it open for our users to pick. There are some options regarding the stiffness method. And we have different load combination, strength, extreme, and serviceability. I'm going to uncheck the extreme for this example. If we go to the view, you can see the load and resistance factors for each standard. These are grayed out. You cannot change them because these are specified in ASHTO. But if you have a standard which is based on ASHTO, you can add a user-defined standard, and then we give you that table. Now it's editable. So you can define a user-defined standard based on ASHTO or any other types of standard. You can define a user-defined standard based on British standard. So we give you different tables that you can modify. Okay, so let's pick ASHTO for this example. Seismic forces, we can turn on seismic. ASHTO does not allow vertical seismic coefficient, so only horizontal. Failure modes, we have external, sliding, overturning, bearing, internal sliding, and crest toppling. I'm going to turn off crest toppling for this example. And reinforcement strengths can be pull-out, tensile, and connection. Methodology, for active earth pressure, ASHTO only allows Coulomb and generalized wedge method. Keep in mind, if you want to define cohesion for your backfill, Coulomb doesn't allow cohesion, but generalized wedge method allows cohesion. So if you want to do to have cohesive soil for your backfill, you should pick the generalized wedge method. For supports, we have simplified method, coherent gravity, and stiffness method. And passive earth pressure, we have one method, so it's grayed out. But if I go back and change, for example, to British standard and go to methodology, you can see that I have way more methods. So based on this dialogue is based on what standards recommend. So if they recommend different methods, we have them available. If they don't, we can just make up methods here and bring them here, while the standards, they don't accept it. So this program is specified for standards. So if there is anything outside of the standards, if we can interpret it based on a standard, we will add it as a feature to the program. I'll talk about it at the end. So I'm going to go back and pick ASHTO again. And methodology, I'm going to stick to Coulomb method and simplified method as well. When I hit OK, it's just based on, everything is going to be based on ASHTO. Then the first step is to define your walls, wall units. Basically, these are the facing wall units. We have modular, since it was a segmental wall, we have modular and wraparound for the units. As I mentioned, we have manufacturer libraries. Our manufacturer library for blocks are ReadyRock and Magnumstone for now. I'm going to use the manufacturer library. So for wall unit 1, I'm going to pick this solid R28T. And I'm going to add another wall unit, and I'm going to change it to this one, R60. So R28 and R60. The difference is just a width of blocks, facing blocks. So these units are created. Then I hit OK. The next step would be to define your wall profile. This is for the case that if you want to do one single segment wall. The beauty about RSWall is it's not limited to a one single segment wall. You can actually create multi-segment walls. Imagine you have corner walls, that you have multiple designs for your wall, multiple walls actually. You can create it in the RSWall program. So we go to the wizard. This wizard is to create a multi-segment wall. You can define numbers, or you can import the numbers into the program. I have them in the text. So this is my soil profile coordinates. So when I hit OK, I get two views, plan view and front view. So this is the front view of my soil profile. I click on next. Here, you can define your wall unit. You can always change it later. This one is uniform for now. You can define the embedment depths. Let's change it to 0.4, for example. You can define the setback for your wall as well. When I click on next, the software, based on my soil profile, is gonna create an automatic segmental wall. So I'll click on next. So for each segment, you can see each segment is selected. We created a wall. You have different options. You can increase the course of the wall. You can reduce it, the height of the wall. The size of the wall depends on the maximum elevation of your soil profile. So if I click on that one, you can see that there should be a block here, but depends on this maximum elevation, we create a wall. So for example, this wall might be too long, 12 meters. So what I'll do, I can split it. Once you click on a split, it's going to create two segments with the same length. And then you can play with them and change the lengths and everything. So now I have 5 different segmental walls. When I click on finish, this wall is created. You can see the 3D view for multi-segment wall. This is the plan view, and these are each segments. When you click on each segment, the 2D segment will be shown. So keep in mind, we don't consider the 3D effect for different segmental walls. So the most conservative case is we assume that they are independent walls. So different segments will be behaved independently. Now, we go back to our soil profile. Now, based on our segmental wall, we have different profiles. As I mentioned, we defined 2 units. Each segment can have, each profile can have non-uniform units. I can change the units, like you can see the size of the block is changing. Or for the entire wall, I can change it to unit 2, and for segment 5, I change it to unit 2 as well. So if I hit OK, you can see that these 2 blocks, these 2 segments, they have wider blocks. If you can see it, it's obvious here compared to the other segments. So that's how you can change the units, facing units as well. As I mentioned, you can always go back to the wall creation and change the profile for each segment and change their segment ends, which is the height or extension of the segment. You can always add leveling path to the base of your wall, different dimensions. Also, you can define the base strength. This base strength is basically to calculate bearing capacity. You can specify the ultimate bearing capacity, or you can define ask the software to calculate it based on soil properties. And there is a table in ASHA and other standards that depends on the applied the contact with the soil. You can pick one. For this example, I'm gonna pick soil on soil for the walls. So next is to go to the soil profile. So you can see that these tabs basically dictate the flow, but you are not restricted that if you don't do this step, you can't go to the next step. You are free to define whatever you want first and then go to the other sections. So for this part, I want to define the back slope topography. As I mentioned, the infinite one is horizontal. The broken one, you can define the angle. And we have an option of user defined that you can define different rows. Let's say 2, 3, 4, and 5. And we do 1, 1, and 2, and 2. So this is the geometry of my back slope. You can apply it to the current segment, or you can apply it to all the segments. If I hit OK, you can go to every segment, and you can see based on the dimension of the segment, this back slope is created. You can do the same thing for front face, user-defined, broken. I just leave it as the infinite. Here you have the option to consider the passive resistance or not. So if you want to passive resistance to go to the calculation of a sliding and other calculations, you can check it on, turn it on, and hit OK. So the passive resistance is considered. Next step would be to define the soil properties. So soil 1, we call it retained. Soil 2, I'll call it reinforced. And soil 3 is going to be foundation. For the retained one, the unit weight is going to be 20, friction angle of 30, soil structure friction angle, which is delta in the standard, is 20, and cohesion of 0. For the reinforced soil, I'm going to change the unit weight to 22, friction angle to 34, the soil structure friction angle 26.5, and no cohesion. And for foundation, unit weight of 23, friction angle of 34, soil structure friction of 20, and we define cohesion of 10 for foundation. We have the coefficient of adhesion for each soil as well. So I'm going to hit OK. Soil properties are created. After creating the soil properties, now you can assign the soil properties. Retain is already purple, so we apply the reinforced. We apply the foundation. There is no leveling path, so the software is going to ignore this part. You can have a different back slope property if you want, or if you uncheck it, the back slope is going to be the same property as the reinforced one. And when you hit OK, you can see that there is no reinforced region because I haven't defined reinforcement yet. So once you define the reinforcement region will come up. You can define constant water table or differential water table in the back slope and front face. For this example, I'm going to do minus 0.5, which is a constant elevation for water. And you can see that this is the blue line. This is the water table. So the water table is added as well. Now, let me save this project on desktop somewhere. It's going to be test folder. So I'm going to call it MSC segmental. Now, the next step would be to define loads for this model. I'm going to go to manage loads. As I mentioned, you can define uniformly distributed loads, blind loads, and point loads, and the live surcharge, permanent load, air surcharge, and unclassified. I'm going to define 3 different types of loads because I have 3 different segments, like different segments. I would like to assign different loads to different segments. For load 1, I'm going to change it to line load, live surcharge, vertical. The horizontal distance would be 2.5. It's going to be 100 kilonewton per meter, and the bearing width would be 1 meter. And I'm going to assign it to segment 1 only. Then I'll go back to load 2, line load 2.5. This one, I'm going to change it to 75 with the bearing width of 1. And I'm going to apply it to segment 2 and segment 3. And the last one is going to be load 3, line load 2.5 and 50, and bearing width of 1. And I'm going to apply it to segment 4 and 5. Correct. When I hit OK, you can see that segment 1 has 100, segment 2 and 3, 75, segment 4 and 5, 50. So it's very easy to apply these laws. Now let's go and define reinforcements. For reinforcement part, I'm going to do GeoGrid. We have GeoGrid, GeoTextile, GeoStrip, metallic grid, a metallic strip, and we have manufacturer libraries for them as well. I'm going to define 2 different reinforcement types. Reinforcement 1, the tensile capacity of 300 kilonewton per meter. Soil interaction, I'm going to use 20. And for friction factor, you have the option to define constant or function of depth. I'm going to do 1.5. and I'm gonna stick to alpha of 0.8, and for connection, I'm gonna do 150. Connection, you have different options: constant, frictional bilinear, and function of depth. And design a standard, you can define them as well. Then we go to reinforcement 2, GeoGrid. This one would be 400 tensile, soil interaction of 22, friction factor of 2, and alpha of 1. It's a stronger reinforcement. And the constant value of the connection of 200. So I hit OK. Now it's time to define your layout. So as I said, you can do uniform and non-uniform. For example, I want to have 8 layers of reinforcement. It can be uniform or non-uniform, and you can define them based on wall course, elevation, and height from the bottom. I do wall course and uniform, so every single block unit has a reinforcement layer. And for this one, I'm going to do non-uniform. I'm going to change the first 4 reinforcement to reinforcement 2, which is the stronger, and the top one is a slightly weaker reinforcement. So if I hit OK, you can see that depends on the height of the wall. They might have 7 or 8 reinforcements. So different types of reinforcement for the wall. Then the next step would be the results step. The computation is very fast. I'm just going to click compute. It's going to compute the results for every single segment. So let's look at the results. First of all, this is the active force wedge. You can just turn it on and off. You can look at the relevant symbols. These symbols are the ones that they are being used with the figure number, with the values. So if you are looking for a specific parameter, you can see what equation it's being used in and what is the value. As I said, this is not a black box. Every information that you want is available. You can look at the analysis issues. Everything is green, so there is no analysis issues for this example. But I'll show you how it works. The most important thing in RSWall, one of the most important things, is the report generator. As I mentioned, you may need hand calculations for your analysis and for your reports. We give you the hand calculation. It's the PDF format. So every single calculation in this program, whatever number that you see here, it's going to be in the report generator. So let me open it, and I'll explain how the parameters go. So project summary, project settings, unit properties, reinforcement properties. But when you go to the results, you can see that list of symbols, the one that we saw in the table that I showed you. For every wall segment, we have the model properties with images, with the parameters, and with the equation numbers, figure numbers, article numbers, that they are in the standard. So this figure 11.10.6.4.4b is from AASHTO. So if you Google it, if you go to AASHTO, you can find this figure and see what parameter we assume based on your inputs. And when you go to the strength limit state, for example, you see the summary of the CDR values, and for reinforcements as well. You see all the external forces being calculated. These are the forces that I showed you at the beginning. Then we go to base sliding. It shows you how the CDR is being calculated and if it's pass or fail. Eccentricity, overturning, bearing, everything is here. All the calculations. For example, for bearing, this is the Terzaghi equation that these parameters, they're coming from Reisner, Prandtl, other references, and we calculate the bearing capacity. So if you see anything wrong in your model, you can just easily come here in the report generator and see what's going on in the hand calculations. And for every reinforcement layer as well. Also, if we go back to our model, this is a table with the minimum CDR for each segment. This is among all the segments, but for each segment, you can see the minimum CDR for that segment as well. You can always filter these results. For example, if you are interested only on external failure, you can look at base sliding, you can look at bearing, You can look at overturning, or you can turn them off and look at connection, pull out, and tensile. So these are the values of the factor of safety based on different failure modes. You can always click here and take the model to a slide. So you can click on open a slide, and it opens the slide software. It directly takes the model to the slide program. You can always save it here. And since it's a multi-segmental wall, it creates a multi-scenario slide file to check for the overall stability. So everything is has been brought here, like support properties. These are the supports that I defined. Soil properties. These are the soils that I defined. Different types of soil. For wall block, it assumes a very high number. And water table is here. And different segments, you can see even the widths of the blocks. And since it's multi-scenario, you can play with these scenarios in a slide. For example, I'm going to select a Spencer and Yambu. And for the last segment, I'm going to change it. The assumption is circular. I'm going to change it to a non-circular method. And you can see that even we define the slope limits automatically. So I'm going to compute this model to look at the overall failure mechanism in a slide. So you don't have to recreate the model. These are directly integrated. So this last stage is a non-circular one. So this is done. And we go to the results. You can see the circular failure surfaces for overall stability. They are all over 2, so it's satisfied. But when it goes to non-circular in the last one, compared to the previous one, it drops. So non-circular failure surface gives lower factor of safety, which is expected compared to the previous one, which is circular. So you can see all these results in the slide program for the same wall as well. Some cool stuff that we have in RSWall and other Rocscience program. You have access to RS Insight. RS Insight is our new, let me use my username and password. Actually, I don't have access to it. It's our new AI-based chatbot at Rocscience, so you can ask your questions. So we have a limited time. I just wanted to mention, you can have a ticket of technical support. You can access to documentation and updates of the program as well. As I mentioned, you can export to the DXF files too. So this one was one example. I'm going to quickly show you another example that I created. It's a Gabian wall. I just wanted to show you for different other types of walls how you can create a RSWall model. And then I'll go and answer there are so many questions, so I'll try to cover the questions as well. Let me open this Gabian example. So Gabian walls, for example, for this example in the project setting, I have like generalized wedge method. Design standard is ASHTO. I have the extreme case and serviceability case, and you can see that the factor of safety is still for strength limited state is 1.39. For wall geometry, that's the important part about retaining other types of retaining walls. So you can see that for wall units, I defined 2 units with different dimensions. And which is a darker one is a shorter, smaller Gabian basket. And I use a non-uniform wall unit, so different units for different rows, and these are different number of baskets. And for geometry part, I define the tilt angle, and we have 6 rows of baskets. In terms of soil properties, back slope, this one is broken. And front face, I consider the passive resistance as well. And the loading is just a distributed load. Since it's Gabian, the reinforcement part is turned off. and we just consider the gravity wall. And these are the results of the Gaussian walls. Um, if I go back and change the property of the, let me do it for the other example. I just wanted to show you something and then we go to the questions. Let's say for the retain one, in the previous example, I changed the cohesion to 5. Then I'll go back to the results and recompute my model. This one is not green anymore and it becomes orange. And if you go to the analysis issues, you can see that it says cohesive backfill are ignored using the Coulomb method, but for generalized wedge method, it is being considered. So this software is smart. So we check everything behind the scene and give you proper notifications and errors and warnings. So if you do anything wrong, we will give you based on the standards. So whatever is mentioned in the standards, we will check behind the scene. This is available in your report generator as well. So these warnings that you see here, you will see them in the report generator too. So it's interactive procedure. Okay, so this was the first version of RSWall. We are actively working on developing different features in the software. So some of your questions, we might also already developed it, or we are developing it. But if you have any question, if you have any suggested features, please feel free to let us know, because this is a new program and we are open about suggestion. We can develop different features in the program, and you're welcome to send your suggestions. Thank you very much and have a good day and night wherever you are.